Who serves whom? Dynamic resource matching in an activity scanning simulation system. This presentation describes a stroboscope simulation model for the familiar barbershop problem where customers have favorites, barbers may not show up for work, and customers may get impatient and leave. This non-construction problem was chosen for a variety of reasons. It is familiar, complex, and yet small enough to be described completely in a relatively short amount of time. It also illustrates two important things. The first is that Stroboscope makes no distinction between resources that serve, such as barbers, and resources being served, such as customers. This is because stroboscope models focus on activities and the conditions under which activities can start. As a result, all resources are simply viewed as prerequisites for activities to take place. Because of this, a stroboscope model can do something unique. It can switch from a mechanism that matches customers to barbers to a mechanism that matches barbers to customers without altering the basic structure of the model. The second reason is that it has been estimated in the literature that it takes 10 to 19 hours of work to model the classic barbershop problem when using a process interaction simulation system. We hope to show that in Stroboscope it requires substantially less time. In this example, a barbershop has three barbers: A, the owner, B, and C. Some of their customers have a favorite barber. 30% of the customers prefer barber B. 10% of the customers prefer barber C. And 60% of the customers have no preference. Notice that no customer prefers barber A, the owner. Customers are also impatient. When a customer arrives to the barbershop, he will first check the overall number of customers waiting in line. If there are more than 6 customers already waiting, he will turn around and leave. An arriving customer who wants a favorite barber will also check to see how many customers are already waiting for that barber. If there are more than 3, he will also turn around and leave. The arrival and service times are as follows. The time between customer arrivals is exponential with mean equal to 12 minutes, and the time to cut a head of hair is also exponential with a mean of 19 minutes. Barbers do not always show up for work. There is a 5% chance that a barber will be absent on any given day. Also, a customer whose favorite barber is absent will turn around and leave immediately. This figure shows the stroboscope network for the barbershop simulation model. The upper half of this network represents a 24-hour clock that controls the day-to-day availability of barbers. Together, the 3 nodes, start, work, and off shift, act like a simple clock mechanism that regulates the daily cycle. At the start of simulation, Q start is initialized with 1 unit of a generic resource called a token. This token allows combi activity work to start at simulation time 0. When work finishes 8 hours later, it releases the token to the starting normal activity off shift. 16 hours later, activity off shift ends and releases the token to the Q start to start the cycle again. Thus, work and off shift follow each other in a continuous cycle of 8 hours of work and 16 hours of off time. At the start of simulation, the 3 barbers are located in Q absent Q. The Q new day contains one resource of generic type token to enable activity start of day to start. Start of day is a dummy activity that removes all barbers from the queue absent queue and releases them to the queue barber queue where they are available for work. If any barbers are absent that day, they remain in queue absent queue. When activity work ends, it releases 3 tokens to queue end day to allow the dummy activity end of day to start 3 times. Each instance of the dummy activity end of day transfers 1 barber from barber queue to absent queue for the overnight break. When off shift finishes, it releases 1 token to the queue new day to allow start of day to start again and bring the barbers back to work. The bottom left part of the network models the arrival of customers. The bottom right part models what happens to these customers when they arrive. They either get a haircut or they change their minds and leave. The QSEC, which stands for sequencer, is initialized with 1 token to allow activity cust arrive, which stands for customer arrive, to start. The duration of cust arrive represents the inter-arrival time between successive customers. When cust arrive finishes, it returns the token to sec and the cycle is repeated. Every time activity cust arrive finishes, it generates a new customer resource that is released either to the queue cust wait, which stands for customers wait, or to the queue cust exit, which stands for customers exit. This choice depends on the queue of customers waiting for a haircut, the availability of a preferred barber, and the time of day. Each customer routed to cust exit is immediately drawn by an instance of dummy activity leave and is destroyed. A customer that enters cust wait joins the queue of customers waiting for service. When a compatible pair of barber and customer are available, activity cut starts and the barber gives the customer a haircut. A customer that has a favorite barber waits in queue until the particular barber is free. If in the meantime a customer arrives who prefers another barber or has no preference, that customer may bypass those in queue and get served earlier. The mechanism for matching customers to barbers or for matching barbers to customers will be described in detail later. We shall now describe the statements for a complete stroboscope model of this barbershop. First, we define the number of available barbers as a problem parameter to allow for sensitivity analysis. Next, we define the resources that flow through the simulation model network. Token is a generic resource that does not have any attributes and is used to initialize and maintain activity cycles like the clock and the arrival of customers. Barber is a compound characterized resource type that represents the barbers. Later on, we shall initialize the queue absent queue with 3 resources of type barber. These 3 resources will automatically be assigned resnum equal to 1, 2, and 3. It should be noted here that resnum, which stands for resource number, is like a serial number that can be used to identify each resource individually. In this case, the barber whose resnum is 1 will represent barber A, the owner. The barber whose resnum is 2 will represent barber B, which is preferred by 30% of the customers. And the barber whose resnum is 3 will represent barber C, which is preferred by 10% of the customers. Customer is a characterized resource type for which we define one property called choice. We also define three subtypes of customer called cust0, cust2, and cust3, each having a value of choice that reflects their barber preference. The value 0 indicates no preference, whereas 2 and 3 point to the barbers with the same resnum. These statements define the attributes of the activities for the clock. Combi activity work is assigned the highest priority because the existence of an instance of activity work is a prerequisite for other combi activities to start. The time units for this model are in minutes. Thus, the duration of work is 8 times 60 to represent 8 hours of work time. The duration of off shift is 16 times 60 to represent 16 hours of off time. These statements bring the barbers to work and remove them at the end of the day. When combi start of day starts, it tries to remove all three barbers from absent queue. Link B3 does this by pointing to and attempting to draw each barber one after another. This process continues until the draw until logical expression for link B3 becomes true, that is, different from the value 0. In this case, it never happens because the draw until logical expression is set to 0 and link B3 cursors and attempts to draw all three barbers. For each cursored barber, link B3 evaluates the logical expression for the DrawWhere statement, and if the result is true, it draws the cursored barber to the starting new instance of start of day. Otherwise, it cursors the next barber and the process is repeated. A barber is drawn only if the random number returned by the function R&D is less than 95%. Thus, on any given day, each barber has a 5% chance of staying in the queue absent queue and not showing up for work. The number of tokens released into queue end day at the end of activity work equals the number of working barbers, which equals n barbers minus the absentees. Each of these tokens will allow a separate instance of activity end of day to start and transfer a barber from barber queue to absent queue as soon as the barber is done with his last customer for the day. These statements generate customer arrivals. The duration of cust arrive is exponential with a mean time of 12 minutes between customer arrivals. The before end statement indicates that when activity cust arrive ends, but before it releases any resources, it should generate, which means it should create, the arriving customer resource. Notice that the term precond allows the action generate to take place only when the logical expression work.carinst returns the value true. The expression work.carinst returns the number of instances of activity work currently going on. Thus, work.carinst returns the value true and a customer is generated only during working hours. The subtype of the customer that is generated is determined by the conditional expression at the end of this statement. This conditional expression uses random sampling to determine which subtype of customer to create, cust0 or cust2 or cust3. These statements route the arriving customers. Once a customer resource is generated, it is released either through link C1 to cast waits, or through link C3 to cast exit. The order in which links are defined in the simulation input file determines which link is used to release resources first. In this model, link C1 is defined first. Thus, only those resources that are not allowed through link C1 will be released through link C3. The release mechanism for link C1 is controlled by the statements shown here. The first two statements define filters that are used to determine whether an arriving customer who has a favorite barber will decide to wait in line or will turn around and leave. In particular, the filter New Cast Choice is used to determine if the barber who is preferred by the arriving customer is absent today, in which case the customer will leave. And the filter Same Choice Casts is used to count the number of customers already in line who prefer the same barber as the arriving customer. In general, when a filter is applied to a queue, it creates a subset of the queue's contents. Thus, when the filter New Cast Choice is applied to queue absent queue, it creates a subset which includes only those barbers in queue absent queue whose resnum equals the choice property of the customer in activity cast arrive. If this subset is not empty, then the barber preferred by the arriving customer is currently absent from work, and the customer should not wait in queue cast wait. Similarly, when the filter Same Choice Casts is applied to queue cast wait, it returns the subset of customers who prefer the same barber as the arriving customer. If that number is greater than 3, then the customer is released through link C3 and exits the system. The release where statement makes use of these filters and allows only those customers that satisfy its logical condition to flow through link C1. This condition first rejects those customers that prefer a barber that does not exist, due to sensitivity analysis on end barges. Then it examines if there are more than 6 customers in cast wait. If so, the new customer is not released. Otherwise, if the new customer does not have a favorite, which means that not a choice is true, then he is released through link C1. Otherwise, a customer flows through C1 only if the preferred barber is not in the queue absent queue, and the customers in the queue cast wait that have the same favorite as the newcomer is at most 3. Finally, an arriving customer who is not allowed to flow through link C1 is released through link C3. The stroboscope statements that should actually follow at this point are the ones that check whether any barber can be matched with a customer or whether any customer can be matched with a barber. These checks are used to make 2 important decisions. The first decision is whether there is a matching barber and customer pair available that would allow combi activity cut to actually start at this point in simulation time. The second decision is which barber and customer should be drawn by a starting activity cut to have a matching pair. Since a detailed description of this portion of the model is one of the main objectives of this presentation, the statements and their detailed explanation will be presented later. Instead, we shall present next the statements that initialize the contents of queues and run the simulation, which ordinarily appear at the end of the simulation model. The init statements define the contents of queues at the start of simulation. Queues sec, start, and new day are initialized with 1 token. Queue absent queue receives 3 barbers that are automatically assigned resnum values of 1, 2, and 3. The simulate until statement runs the actual simulation until its logical expression becomes true. In this case, until the simulation clock time, sim time, exceeds 124-hour days, which are expressed in minutes. Finally, the report statement produces the standard simulation output report. These statements match the customers in the queue cast wait to the barbers in the queue barber queue to allow activity cut to start and draw the correct resources. The statements shown here examine first each of the available barbers and then try to find the matching customers for that barber. Later on, we shall present similar statements that examine first each of the available customers and then try to find the barber who matches that customer. Combi activity cut can start when the enough expressions for link C2 and B5 are true. C2 has the default enough expression that returns true when queue cast wait is not empty. This means that resource matching for both barbers and customers is performed by the enough expression for link B5 that draws barbers. The enough expression for link B5 makes indirect use of two filters, matched customers and matched barbers, that cross-reference each other and create a chicken and egg problem. This problem is solved by first defining matched customers with a dummy filter expression that is redefined later. Once the name matched customers is defined, it may be used to define the filter expression for matched barbers. The actual filter expression for matched customers references the filter matched barbers, and for this reason is defined later by the statement filter exp. This way, it is possible for two filters to reference each other. It is this ability to define cross-referencing filters that makes extremely complex resource matching possible. The expression barberq.matchedbarbers.count returns the number of barbers in barber queue that belong to the subset barberq.matchedbarbers. The filter matchedbarbers creates this subset by cursoring each barber in the queue barber queue to determine whether it should be included in the subset. This decision is made by the value of castwait.matchedcustomers.count, which counts the number of customers in cast wait that can be served by the barber cursored by the filter matched barbers. To see how this process works, let us consider the following example. Suppose that the queue barber queue contains barbers 1 and 3, and that queue cast wait contains 4 customers with res num 11, 12, 13, and 14. When the filter matched barbers is applied to the queue barber queue, it cursors the first barber in queue that has res num equal to 1 and applies its logical expression to see if this barber passes the filter. The arrow in the figure represents the filter's cursor or pointer. The logical expression for the filter matched barbers returns the count of the number of customers in the subset castwait.matchedCustomers. To count the number of matched customers, we must first apply the filter matched customers to the queue cast wait and create the subset of those customers who can get a haircut by the barber pointed to by the filter matched barbers. When the filter matched customers is applied to the queue cast wait, it cursors the first customer in queue that has res num equal to 11 and applies its own logical expression. This logical expression allows a customer to enter the subset if its choice is 0, which means that this customer does not have a favorite barber, or if the customer's property choice matches the rest-num property of the barber pointed to by the filter matched barbers. For example, the first customer in the queue cast weight has a choice property equal to 2. This means that he prefers the number with rest-num equal to 2. The barber cursored by the filter matched barbers, however, has rest-num equal to 1. As a result, the customer with rest-num 11 does not enter the subset of customers that can be matched or served by barber 1. The filter matched customers then cursors the second customer in the queue cast weight that has rest-num 12 and again applies its logical expression. However, this customer's choice is 3, which is different from 0 and different from 1. Thus, this customer with rest-num 12 does not enter the subset of customers that can be matched with barber 1 either. The filter matched customers then cursors the third customer in the queue cast weight that has rest-num 13 and choice 3. This customer is identical to the previous customer, and so he does not enter the subset. Finally, the filter matched customers cursors the fourth customer in queue cast weight that has rest-num 14 and choice equal to 0. Choice equal to 0 means that this customer does not have a favorite barber, and as a result, the logical expression for the filter matched customers returns the value true. Thus, the subset created when the filter matched customers is applied to the queue cast weight for the first barber in barber queue contains only one customer, the one with rest-num equal to 14. The expression castWeight.matchCustomer.count then returns the number 1, which has the logical value true. This means that barber 1 is included in the subset barberQ.matchedBarbers. The filter matched barbers then cursors the next barber in the queue barber queue and repeats the process of evaluating its logical expression. This time, the subset castWeight.matchedCustomers contains 3 customers, the ones with rest-num equal to 12, 13, and 14. Customers 12 and 13 prefer barber 3, and customer 14 has no favorite barber. Because the count of customers in this subset is 3, barber 3 is also included in the subset barberQ.matchedBarbers. Thus, in the end, the subset barberQ.matchedBarbers includes both barber 1 and barber 3. The enough logical expression for link B5 is the count of the barbers in the subset barberQ.matchedBarbers, which in this case has the value 2, which also represents the value true. This means that there are enough matched barbers and customers to create a new instance of activity cut. The new instance of activity cut must now draw the appropriate resources through its incoming links. This process begins by first drawing a barber through link B5. The barber to be drawn is not necessarily the first barber in line, but rather the first one that can be matched to the customer in cast weight. Once the appropriate barber is drawn, then the new instance of activity cut needs to draw the first matching customer through link C2. The DrawWhere logical expression for link B5 is identical to the filter expression for matched barbers. To determine which barber to draw, link B5 cursors barber 1 and evaluates its DrawWhere logical expression. Because this DrawWhere expression is identical to the filter expression for matched barbers, it returns a subset with customer 14 in it, whose count of elements is 1. Thus, link B5 draws Barber 1 to the newly created instance of activity cut, and the drawing process through link B5 ends. The next step after drawing a barber through B5 is to draw a matching customer through link C2. This does not require the use of filters because the new instance of activity cut has already drawn a barber and makes it easy to refer to its resnum through the variable cut.barber.resnum. The drawing process through link C2 is illustrated in this figure. Link C2 cursors the first customer in queue cast weight and evaluates its DrawWhere expression. The DrawWhere expression for customer 11 returns the value false, so this customer is passed over. The DrawWhere expression for customer 12 and for customer 13 are also false, so these customers are also passed over. Finally, the DrawWhere expression for customer 14 returns the value true, so customer 14 is drawn by the new instance of activity cut. After the new instance of activity cut receives Barber 1 and customer 14, it proceeds to determine its duration. For the research situation in this example, it is clear that after Barber 1 is removed from queue Barber Q, the enough attribute for link B5 will again be true because Barber 3 can be matched with customers 12, 13, or 14. Thus, activity cut will be able to start the second time and create another new instance. The second instance of activity cut will draw Barber 3 and customer 12. When these resources are drawn, Barber Q will become empty, and no more instances of activity cut can be created at this simulation time. These statements illustrate how to reverse the modeling perspective. This time, we will first examine each customer in queue cast weight and then find the matching barbers in the queue Barber Q. These statements are very similar to those used earlier for matching customers to barbers. This figure shows the same example as used earlier to illustrate how the new stroboscope statements work. The logical expression for the enough expression for link C2 requires that we count the barbers in the subset that is formed by applying the filter matched customers to the queue cast weight. When the filter matched customers is applied to the queue cast weight, it cursors the first customer in line and evaluates its logical expression. The logical expression for the filter matched customers then applies the filter matched barbers to the queue Barber Q and returns the number of barbers in the subset that results. When the filter matched customers cursors customer 11, the resulting subset of barbers is empty. So customer 11 does not pass the filter and is not included in the subset formed by applying the filter matched customers to the queue cast weight. When the filter matched customers cursors customer 12, the resulting subset of barbers contains Barber 3. So customer 12 passes the filter matched customers. Then the filter matched customers cursors the next customer, which is customer 13. The resulting subset of barbers is again the same and contains Barber 3, so customer 13 also passes the filter matched customers. Finally, when the filter matched customers cursors customer 14, the resulting subset of barbers contains both Barber 1 and Barber 3, so customer 14 also passes the filter matched customers. In the end, the subset formed by applying the filter matched customers to the queue cast weight contains customers 12, 13, and 14. The enough expression for link C2 counts the number of customers in this subset and returns the value 3, which is true. In other words, there are 3 customers that can be matched with a barber, so there are enough to create a new instance of activity cut. At this point, activity cut has created a new instance and needs to draw a customer from the queue cast weight through link C2. This figure illustrates the process by which link C2 will draw a customer. This begins by link C2 cursoring the first customer in queue cast weight and applying the logical expression of its DrawWhere attribute. This logical expression is identical to the logical expression for the filter matched customers that was used by the enough attribute of link C2. As a result, the subset of matched barbers for customer 11 is empty and customer 11 will not be drawn. Link C2 will then cursor customer 12 for whom the subset of matched barbers includes barber 3. Thus, the new instance of activity cut will first draw customer 12 and then barber 3. Notice that it is important in this case that to draw in the proper order, link C2 should be defined before link B5. At this point, the enough expression for link C2 is re-evaluated and returns the number of elements in a set that contains only customer 14. This is enough for activity cut to create a second instance that will draw customer 14 first and then barber 1. No more instances of activity cut can be created because barber queue is now empty. Notice that the 2 instances of cut are created, i.e. draw resources, in reverse order from that where customers were matched to barbers. Conclusions. The 2 barbershop models that match customers to barbers and vice versa produce identical results, even though the roles of barbers and customers are reversed. This is because in the actual simulation models, it is impossible for more than one instance of activity cut to start at the same simulation time. The reason for this is that, at most, only one instance can start when either a customer arrives or when a barber becomes free. The barbershop example illustrates the power of Stroboscope to model complex resource matching and activity startup conditions, and even reverse the role of resources without changing the basic structure of the simulation network. Finally, it is important to emphasize that there are many resource matching problems similar to this example that can be classified into a few standard types. This means that the same mechanisms for resource matching can be reused from one model to the next, and this can reduce significantly the required effort to develop new simulation models.